Uh, Good morning, good afternoon, everyone. So today I'll be presenting a work titled as Evidence-Based Reliability Estimation in Deep Neural Network using Dempster Shafer Theory. So the main idea of this work is to look inside a deep neural network and estimate how reliable its internal components are. Instead of only looking at final accuracy, we analyze neurons and weights as evidence source and use Dempster Shafer Theory to measure belief conflict and uncertainty. So here is the overall structure of the presentation. I will begin with the background and motivation, then explain the research gap and problem statement. After that, I will introduce Dempster-Shafer theory and how it is used in our methodology. Then I will discuss internal reliability modeling, the experimental setup, and finally the results. Uh, let's start with the background of this work, which is basically based on the fact that deep neural networks are powerful, but their internal decisions process is difficult to interpret. In the study, we show that the Dempster-Shafer theory can be used to quantify the internal reliability of a deep neural network in an interpretable way. One important observation is that neurons do not always behave consistently. Some neurons support correct predictions, while others may contribute to incorrect predictions or conflicting evidence. On the other hand, weight structures can remain relatively stable even when the model is perturbed. So this helps explain why pruning can sometimes remove a large portion of the model while still maintaining good accuracy. So the key insight is that internal reliability can provide a principled basis for pruning, trust, estimation, and security analysis. Uh, so deep neural network have become central to modern AI system. They are widely used in computer visions, natural language processing, medical diagnosis, autonomous systems, and security-related applications. The reason why deep neural networks are powerful is that they can learn hierarchical feature representations from large-scale data. Lower layers usually learn simple features, while deeper layers learn more abstract and task-specific features. However, even though DNNs perform very well, understanding their internal behavior remains a major challenge. The major limitation is the lack of transparency. Deep neural networks often behave like a black box system. We can observe the input and output, but it is difficult to understand what is happening internally. Uh, Specifically, the behavior of the neurons and weight structure is not directly interpretable or measurable using traditional performance matrices. This creates difficulty in high-stakes applications where we need not only high accuracy but also trust explanations and reliability. So the research gap comes from the tension between high accuracy and lack of trust. DNNs are already used in healthcare autonomous systems and security critical environments. In these domains, a model cannot simply be accurate, it must also be reliable and explainable. However, current methods mostly explain the final prediction or measure prediction confidence. They do not fully explain how internal components contribute to the final decisions. So, even if a model gives a correct output, we may not know whether the internal reasoning was stable or unreliable. So the deeper issue is that existing models cannot clearly explain why a prediction is made or verify the internal decision process. A model may fail because of unreliable neurons, weak or noisy weight structures, or sensitive to small perturbations such as adversarial attacks. Traditional evaluations focuses on external performance such as accuracy, loss, precision, or recall, but these matrices do not tell us which neurons are reliable, which weight are stable, or where internal conflict exists. This motivates the need for an internal reliability measurement framework. So the motivation of this work is to improve trust, pruning, and security in deep neural network. If we can measure which internal components are reliable and which are conflicting, then we can make better decisions during pruning. So instead of blindly removing small neurons or random structures, we can remove components that shows unreliable or conflicting behavior. This can show model compression, preserve accuracy, and also help detect abnormal or malicious behavior inside the model, such as backdoor affected neurons. The main problem is that DNNs are powerful but internally opaque. So existing explainability and confidence estimation methods usually focus on input-output behaviors. They may explain which input behavior influenced the output or how confident the model is in a prediction. However, they fail to analyze internal components such as neurons and weights. So they also do not measure internal trustworthiness or capture agreement and conflicts inside the network. So the central research question is how can we quantify the evidence contribution and trustworthiness of neurons and weights inside a deep neural network. So this question guides the proposed framework. Dempster theory is a framework for reasoning under uncertainty and incomplete information. So, unlike traditional probability, which assigns probability to individuals' outcomes, Dempster theory can assign belief to a set of possible outcomes. This is usually because in many systems, including neural networks, we may not have complete certainty. Some evidence may support one hypothesis, some may support another, and some may simply represent uncertainty. The key concepts are the frame of discriminant, mass function, belief, and plausibility. In our case, this theory allows us to represent support, conflict, and uncertainty inside a neural network. The proposed methodology uses Dempster-Shafer theory to model internal components of a DNN as evidence source. Neurons are treated as activation-based evidence source. Their activations are analyzed to determine whether they support correct or incorrect prediction. Weights are treated as structural evidence source. Their reliability is measured by applying perturbation and observing the impact on model performances. After computing neuron level and weight level evidence, we combine these using Dempster-Shafer rule of combination to estimate overall internal reliability. To understand Dempster-Shafer theory, here we have intuitive example. Consider two people observing a person entering a room. The question is, what is the color of the person's shirt? The possible outcomes are red and blue. So person 1 thinks the shirt is red with 70% belief but is still 30% uncertain. Person 2 thinks the shirt is blue with 60% belief but is 40% uncertain. Instead of forcing one final answer immediately, Dempster-Shafer theory allows us to represent partial belief, uncertainty, and conflict between the two observations. Here we combine both observations using Dempster rule. First, we calculate the conflict between the two sources of evidence. Conflicts occurs when one source supports red and the other supports blue. Then we normalize the remaining evidence and compute the final belief values. The final result gives belief for red, belief for blue, and remaining uncertainty. This example is important because neural network components can behave similarly. Some neurons may support the correct prediction, others may support incorrect behaviors, and some may be uncertain. Traditional pruning methods usually remove weights or structure based on magnitude, randomness, or sensitivity. The common assumption is that smaller weights are less important, but this assumption is not always correct. Traditional pruning ignores internal reliability. It may remove useful components and keep unreliable or malicious ones. Also, traditional pruning is mainly designed for compression, not security. So our DS-based reliability pruning is different. It models neuron belief, weight reliability, conflicts, and uncertainty, which allows us to identify conflicting or infected neurons and remove them in a targeted way. So the goal is not just compression, but trustworthy and security-aware pruning. The core idea is to treat internal neural network components as evidence sources. Neurons provide activation-based evidence. We observe how strongly each neuron activates for correct and incorrect predictions. Weights provides structural evidence. We test whether weight groups remain stable when small perturbations are applied. The pipeline has five main steps: extract neurons activation, compute neuron level belief, apply weight perturbation, compute weight level belief, and fuse the evidence using Dempster's rule. The final output belief includes belief, conflict, and uncertainty. For neuron level reliability, the goal is to measure how each neuron contributes to correct and incorrect predictions. First, we collect neurons activation for each sample. Then we divide the data into correctly classified and incorrectly classified samples. For each neuron, we compute the average activation for correct prediction and the average activation for incorrect prediction. If a neuron is more active during correct prediction, it supports correct classifications. If it is more active during wrong prediction, it contributes to conflict or error. The key takeaway is that neurons' behavior is not uniformly reliable. Some neurons provide useful evidence while others produce conflicting internal evidences. For weight level reliability, the focus is on structural stability. Instead of analyzing activation behavior, we group weights connected to each neuron and apply a small perturbation such as Gaussian noise. Then we compute the baseline accuracy with the accuracy after perturbation. If the accuracy drop is small, the weight group is considered reliable. If the accuracy drop is large, the weight group is unstable. The observation from this work is that weight show very high belief and low conflict, meaning they are more structurally stable compared to neuron activation behavior. Now we have the experimental setup. So the purpose of the first experiment is to validate the mathematical correctness of the TS framework. A small synthetic data is used with 10 samples and 3 neurons. Out of these, 6 predictions are corrected and 4 are incorrect. The activations and prediction outcomes are manually assigned, so the belief masses and conflict values can be directly checked. The result match the Python implementation exactly, confirming that the TS fusion process is working correctly. The second experiment analyzes real neuron behavior as evidence sources. Hidden layer activation are extracted using PyTorch forward hooks. Then the sample are grouped into correct and incorrect predictions. The belief masses are computed based on activation statistics, and Dempster Shafer fusion is applied across neurons. The result shows moderate belief but high conflict. This means that neurons provide mixed evidence and often disagree internally. The key insight is that neurons level behavior is inherently conflicting and not always reliable. The third experiment evaluates the structural reliability of weights. Weights are grouped per neuron and small perturbations are applied to them. Then the accuracy before and after perturbation is compared. The result shows very high belief and low conflicts. This means that the weight structures remain relatively stable even when a small noise is introduced. The important finding is that weights behave as more consistent evidence source compared to neuron activation. The fourth experiment tests whether the reliability measurement are consistent across different conditions. The step includes five-fold cross-validation, multiple random seeds, and increasing perturbation level. The result shows that neuron level belief varies and conflicts remain high. In contrast, weight level belief remains stable and conflict remains low. This suggests that the TS-based reliability measures are reproducible and can capture consistent internal patterns across experiments. Now the result and analysis. Uh, this table shows the neuron level results. Here, mu represents the average activation of a neuron for correctly classified samples, and mu omega represents the average activation for incorrectly classified samples. For example, N3 has high mu and low mu omega, meaning it strongly supports correct predictions. N2 has higher activation for incorrect prediction, which suggests it behaves as a conflicting neuron. So overall, the neuron level evidence is inconsistent, which supports our argument that neurons can produce conflicting internal signals. This slide directly compares neurons and weights. The neurons level belief is around 0.47 with conflicting around 0.50. This shows that neurons are unstable and internally conflicting. In contrast, weights have belief close to 1 and conflicts around 0.15. This shows that weights are much more stable. The critical finding is that the internal reliability is not uniform across the network. This supports the need for component-specific reliability modeling instead of one-size-fits-all pruning. This slide shows how DS weights evidence mass changes as perturbation strength increases. As perturbation increases, the belief that weights are reliable decreases. At the same time, the belief that weights are unreliable increases. This is expected because stronger perturbation creates more structural degradation. The important point is that DS belief can capture this degradation in a measurable way, So belief mass can be used as a reliability indicator under stress. This slide compares pruning accuracy under perturbation. The observation is that non-DS pruning loses accuracy more quickly as perturbation increases. In contrast, DS-guided pruning maintains higher accuracy. This means that proposed method is more robust because it removes unreliable components while preserving stable and important ones. The main takeaway is that DS-guided pruning improves robustness under noisy or perturbed condition. This slide shows the relationship between model size and sparsity. As sparsity increases, the model size decreases significantly. This is important for scalability, especially when deploying a model on resource limited systems such as IoT or edge devices. The important observation is that DS-guided pruning can reduce model size while keeping accuracy stable. This means that method supports both compression and performance preservation. This table summarizes pruning performance. The baseline model has 0% sparsity and accuracy of 0.917, where the non-DS pruning at 70% sparsity accuracy drops to 0.846. This shows that traditional pruning removes some useful components. However, DS-guided pruning at 70% sparsity achieves 0.926 accuracy, which is even slightly better than the baseline. This shows that reliability-aware pruning can remove harmful or unreliable components while preserving the important ones. Uh, so that concludes my presentation. So for your summary, I want to say that this work shows that how Dempster-Shafer theory can be used to estimate internal reliability in deep neural networks. So the main findings are that neurons behavior is often conflicting, where the structures are more stable, and DS-guided tuning can improve robustness, scalability, and trust. Thank you for the attention.